Welcome to the Digital System Design course. Myself, Dr. Rajan Singh, Associate Professor, Department of Electronics and Communication Engineering, MLR Institute of Technology, Hyderabad. About the course, this particular course will provide the participants a strong foundation in the core fundamental of digital circuits. It will also help them to learn different number systems, Boolean algebra, combinational circuits, sequential circuits and its design and analysis. In the last, we will also discuss about the finite state machines. This particular course nowadays will also require that a student must learn hardware description languages, VHDL or Verilog. So the third point, that's a Verilog hardware description languages. All the textbooks coming these days are inherently covered this particular topic also. Although in this particular course we will not cover here this one, but we shall separately record this particular course in a separate video. But this one is a very important thing. After learning all digital circuits and other associated circuitry, students must learn hardware description languages so that they can understand how these hardwares or how these digital circuits are going to be implemented and going to be connected through the VLSI design cycles. What are the intended audience? So this particular subject is generally taught in electronics and communication engineering and related branches, also computer science and engineering, electrical engineering related branches, and generally this particular course is being taught in second year of their 4-year graduation course. What the prerequisite of this particular course required, although the things are from basics only, but for the implementation of digital circuits at the electronic component level, students must have a basic idea how the PN junction diode, bipolar junction transistor or even a MOS transistor works, what is the symbols they have and how the basic operation, that's working of these electronic devices. So this will help them to understand how a particular logic circuit is being implemented at the electronic component level. So the first natural question came into the picture, that why this course? So looking at the surroundings and current electronics age in our day-to-day life, starting from household to the markets and to the defense, to the different areas which touch our human lives, digital circuits are everywhere. And that's digital circuits are dramatically changing the whole world. That means everything is going to be digital day by day. That means how these digital systems work, that's some basic questions remains, and undergraduate of engineering discipline must understand that how these digital systems work, so that they can gain a confidence and also opens them exciting career opportunities. Why so? Because if you do understand how these circuits work and how existing conventional system works, so that you are going to change, we are going to implement, replace the conventional system with the new digital system. The third point is also quite important. The above statement is equally applicable to all undergraduate course of electronics, computer and other related streams. That means one cannot think like this particular digital system design looks like it's a course for the electronics and related branches only, but please note that this particular course is equally important for almost all branches of engineering. Maybe some exceptions for the mechanical or chemical or other branches, but this particular course is equally important for all branches of engineering discipline. Driving factor of the motivation for this particular course is also this particular point, that need of digital designers, engineers with strong computer science skills are increasing rapidly. That means you have a computer science background, you may have electronics engineering background, coding skills and all that, and you also understand how digital circuits works, how they are going to be applicable in any existing conventional system, that these type of technocrats, these type of engineers are very much demand in the current corporate sector. What are the things available right now? So some reputed and well-known companies, MNCs type like Honeywell, ST Microelectronics, microchip technologies, NXP semiconductor, Qualcomm technologies. This particular thing is quite overlapping with the field of semiconductor and VLSI, because these companies may work in core electronics, core semiconductor, or only digital circuits. That means area is quite wide, and companies as per their customer base, as per their expertise works. But in in almost all companies, the engineering graduates which are equally good in digital as well as good in programming languages are going to be best suited for these companies. What are the textbooks and references that's recommended? The first one, Morris Mano, Digital Design. This is the most widely used book across the globe for the digital system design, digital course. The second book is also very interesting. That's author name Frank Wahid, a digital design with RTL, register transfer level design. This particular course, although this first course, Morris Mano also, and what we said minutes ago, that nowadays whatever the books are coming for this particular course, they inherently cover the hardware description languages, HDL also. That means this is the need of the hour, this is the need of the time, that apart from the learning digital circuits, students must also learn very hardware description languages. So that will help them to design and coding how electronic circuits, how hardware circuits can be coded. The last book is also very interesting. That's a digital design, Jacob Wackerly, and all these books are widely used across the various reputed and good universities. We will again discuss the same topic, like 5 digital systems. So as we discussed earlier in last slide, that conventional systems are very rapidly going to replace by the advanced digital systems. So what advantages what digital systems offers? The first point is more flexibility. That means if you replaces a conventional system with a digital system, it's not the end of that particular system. That means that the digital system which replaces the conventional system again can be tuned for some other features, can be added, can be modified for other future requirements, and that's why it's called more flexibility. That means this particular system offers more flexibility. It can be redesigned again with a minimum effort, with a minimum cost. That's why the most important thing is that digital systems offers more flexibility. Again, improved reliability. That means same set of inputs if we are going to apply and we are getting some output. So digital systems offers improved reliability. That means same set of inputs, if we are getting an output after some time under different conditions also, if the every other variables are same, we can expect that reliability is going to be better as compared to the existing conventional systems. That means same input, for same inputs, same output is going to be produced. The third point also interesting one, lower cost. Although it looks like that primary cost will be going to be high for a replacement of existing system with a digital system, but as hardware cost of the digital systems are going down in the recent years and expected to go further down, so it is expected that if the system is going to be implemented at large scale, then overall per unit cost will be also low as compared to the conventional systems. Here we also like to discuss one example. In this particular example, automatic temperature control system is there, in which we used conventional sensors to check the temperature of this particular chemical. Maybe chemical in a plant, some chemicals are there and that must be maintained some temperature. So this particular sensor physical quantity that's going to be transferred into analogous electrical quantity with the help of thermal transducer, and that in IO interface is there. Then it goes to the microcomputer, and then if the sense quantity is going to be lower or higher with respect to the reference, suitable controls will be given to the control signal, and then the heater is going to be turned on or turned off as per the requirement. So this particular system is going to take care of a particular unit, of maybe a single unit, one unit only. But please note that I can replicate this particular system for the whole plant only. By replicating this particular one, I can modify, I can add some features, some other complex features also in this particular system, and that's why we have talked about it offers more flexibility as well as reliability, and that's what the systems are. Here also we have the video cassettes which we used earlier. Look at the size and capacity also. Size was very big, but the capacity was less only. But as the technology improves and these things replaced by a hard disk, and nowadays this hard disk also replaced by some semiconductor memory. So look, the size is going to decrease, at day by day. This is a specific example for semiconductor memory, although the most of the things works like this one only. So size is going to decrease, but the feature wise things are going to be increased. Feature wise, here we are concerned with the memory size. Speed also going to be very much high as compared to the previous one. You can also relate this particular one with the flexibility and reliability. Here, whatever you have recorded, the tape has been recorded with the event, with the content. Altering the content and retrieving the content is not going to be easy as compared to the present date drives. Any content you can modify, you can add, you can delete very easily in a fast manner also, and this is how the technology is going to evolve. That means feature wise it's going to be great. At the same time, cost also going to be in initial days, once a new product came, cost may be high, but as technology and its large scale production goes on as per the demand, its cost also set to bound to go down only, and that's why it's a win-win situation for the companies as well as for the customers. The first formal topic we will going to start with the name as number systems. So conventionally in day-to-day life we use decimal number system. The first one, we all are familiar with this particular one. Two things we will introduce here. First one is base or radix. That means what the number we are talking about, what is the base of that particular number. Although since we are day-to-day life or for all our number requirement, we use only decimal number system, so we don't bother to mention the base or radix of that particular system. That means if I am going to say that its number is 123, so I don't bother to write down the base of the system, that base is 10 only. That means 10 itself means that how many numbers we are using. Everyone, we all know that in decimal number systems, numbers are going to vary from 0 to 9. That means total 10 numbers are there, and that's why the base or radix of the decimal number system is 10 only. Place value, we are also very much familiar. It's also called positional number system. So let's suppose a number is 1734 is there. So we can expand as per the position of the bits. So 4 having position 0, then 3 having position 1, 7 position 2, and then 1 position 3. And that's why I can expand this number 1734 like 1 into 10 power 3, that's 1000, 7 into 10 power 2, and then 3 into 10 power 1, and 4 into 10 power 0. If I am going to add this number, we will get the left hand side number exactly. So in general, I can say that a number system, decimal number, can be expanded like D1 10 power 1, D0 10 power 0. The number is like this one. The number expanded here is like D1, D0, point, D of minus 1, and D of minus 2. So I have expanded this number as per the position. So that's why I have written D1. Please note that this D0 has position 0, this has 1, and since these two bits digits D of minus 1 and D of minus 2 appears right hand to the decimal point, so they have a position minus 1 and minus 2, and that's why D1 multiplied by 10 power 1, D0 multiplied by 10 power 0, D of minus 1 multiplied by 10 power minus 1, and D of minus 2 multiplied by 10 power minus 2. So this is all about the decimal number system. Now come to the binary number system. Since The course is digital system design. That means we are talking about the digital circuits, and digital circuits are when we are going to explain or when we are going to follow the number system as a binary. That means logic systems we are talking about. That means it may be high, it may be low, or it may be 1 or 0. Both are analogous only. So that's why binary systems facilitates us to understand and explain digital systems more conveniently, and that's why we use binary number system for explaining digital systems or circuits. So we establish that base or radix will be equal to the numbers used in that particular system. So binary number system we are using 0 and 1. So total number is 2 only, and that's why radix or base of the binary number system will be 2 only. Only 2 conditions, digital systems, that's why we use this binary number system. Similarly, this particular binary number, a number we are saying that it's a 101. So if it's a if I am going to mention, look, please note that this 101, this number may be a decimal number also, but if I am going to specify that no, this is the number written in decimal number system only, so I have to mention that base is 2. Then this is evident that this number belongs to the binary number system. Otherwise, by default, we take a practice like if the base is not defined, we take it as a decimal number system only. So the number same can be expand like this one, again as per the position of the bits. So 1, it's a base is 0, this is 1, this is 2, this is -1, this one is -2, and this one is -3, and that's how it has been expanded. 1 into 2 power 2 extreme left bit, then 0 into 2 power 1, then 1 into 2 power 0 dot came, that means decimal point came, 0 into 2 power -1, 0 into 2 power -2. Please note that 2 power -1 is equal to 0.5, 2 power -2 it's a 0.25, and the last one is 1 into 2 power -3, -1, -2, -3. This is how a number written in binary number system is expanded. The other one which is quite useful is octal and hexadecimal number system. In octal number system, we use numbers as the name suggests 0 to 7, 8, and that's why the base of radix of octal number system is 8 only. And in hexadecimal number system, we use the numbers from 0 to 15, that means total 16, and that's why the base or radix of this number system is 16. Binary and hexadecimals, binary which we have discussed earlier, binary and hexadecimals numbers are more commonly used due to the direct compatibility. Direct compatibility means binary we talked about, that's a 2, and hexadecimal, that's a 16. So 2 power 4 is 16, and that's why there is direct compatibility between the two numbers. One more thing is there, hexadecimal numbers offers very compact representation. Please note that hexadecimal numbers offers very compact representation. Look at this number. This number is 16-bit number written in the binary, and look at the hexadecimal representation, how it has been represented. We will discuss later in the slides, but please note that how compact hexadecimal number system is able to represent the binary number system. Since we have established the direct compatibility, 2, 4, the 2 power 4 is equal to 16, 2 binary, 4 that's a hexadecimal number. That's why each 4 digits represented by a single number in hexadecimal number system, and that's why all 16 bits in the binary appears as 4 bits only in the hexadecimal number system. Here also the same thing is represented, how the things has been represented. We will discuss all others, octal and hexadecimal number systems, in detail also. Here is the detail. So first one, conventional only, everyone is using this particular one, that's a numbers represented from 0 to 15, decimal number system, 0 to 15, base is 10. We have discussed this one because the numbers we are using from 0 to 9. Okay, now come to the binary number system. Binary number system, that means the number constituents are 0 and 1, and it is represented like this one, 0 to 15. It's a 0 and it's a 15. Look at the relationship. Okay. Then octal number system, 0 to 7 only. So from here to here it's a 7 number. But when I am going to represent the number 8, I don't have the digits for this particular one because only 0 to 7 are there. So again, likewise we use for this decimal number system 0 to 9, then 10, 1 0. Then again it's a 1 0 for the octal number system. Look, all the highlighted numbers, 0 to 7 it done, 0 to 9 this is done for the decimal number system. Now subsequent digits are made using the previous digits only. In the next lectures we will also justify that how this 1 0 is equivalent to 8 in the decimal number system. That means 1 0 written in the octal number system is equal to 10 is equal to 8 in decimal number system, when we will discuss the conversion of codes from one base radix to the other. So what I was saying, that up to 7, 0 to 7, all digits have been consumed. Now next digits are framed using 0 to 7 digits again, and that's why up to here. Here also we can easily justify after going code conversion lectures that 1 7 written in octal number system is going to be equal to the 1 5 in decimal number system. This we will discuss. Similarly, come to the hexadecimal number system. Number constituents are 0 to 15 and that's why the base is 16. 0 to 9, these numbers are taken from the decimal number system, same only. That means representation of digits from 0 to 9 in the decimal as well as in hexadecimal are same. But the numbers after 9, that means 10, 11, 12, 13, 14, 15, these numbers are represented using alphabets borrowed from the English alphabets, that's a A, B, C, D, E. That means this is represented as 10, 10 is represented by A, 11 is represented by B, and similarly 15 is represented by 5. That means in hexadecimal number system, to represent 15 numbers 0 to 9, it looks like 0 to 9 digits are taken from the decimal number system, and for the rest representation we have taken alphabets A to F for the 10 to 15 representation. So similarly we can also, after going through the code conversion, we are going to justify that F written in hexadecimal number system is going to be 15 in decimal number system. This we will discuss once we will complete the code conversion in lecture 2. This is introduction of digital system design and introduction of number systems in lecture 1. Thank you all.